Here we have maybe two sets of readings of blood pressures for two different individuals. Now I'll note that both of these have an average pretty close to 140. The average blood pressure is about the same for both individuals. Which individual do you think is healthier as far as their blood pressure goes? Can you tell a difference? Ponder that for a minute. Pause and ponder and come up with an answer before you listen any further. Okay, now I would say that this person is healthier than this person because, see, this person is all the way up to 193 and down to 94. Whereas this person only goes up to, what, 156 down to 128. Okay, 94, if this is systolic reading, is not good, and 193 is definitely not good. 94 is probably better than 193, but if you got a blood pressure of 94, it's hard to be up and walking around. You pass out. 193, you probably have a, well, you don't necessarily have a stroke, but that's a high blood pressure, and that does damage. As long as your blood pressure is up in this range, it does a lot of damage. Or does damage much more rapidly than it does in the lower elevated ranges. Now, one way of comparing these distributions, they have the same mean, but there's an obvious difference. Not just different numbers, but difference in the nature of the distribution. And the difference here is that this thing has a range of almost 100, and this thing has a range of only about 28. The range is from the lowest to the highest, lowest to the highest, and that's one measure of how much a distribution is spread out. So, range measures spread of a distribution. And another thing that measures the spread is the standard deviation. Also measures spread. Now the range is pretty easy to understand, and the standard deviation really isn't that hard to understand. It's a little bit hard to understand why we do the calculation exactly the way we do it, but it isn't hard to see that this calculation is going to measure the spread of a distribution. The definition of standard deviation, it's the square root of the mean of the squared deviations. Now what in the world does that mean? Well, I'm going to try to show you here. So, in the first place, let's take these 6 blood pressure readings, the first person. We don't even want to talk about the second, although you might want to calculate those figures also. If we add these up, we get 840. That's the sum of the x values. The average or mean is what we get, the total divided by the number. That's the 840 divided by the 6 that we added, and that gives us a mean of 140, which is nice and convenient. And you can add those up and check my arithmetic. It might be wrong. In any case, if we assume that the mean is 140, then what's the deviation of each of these numbers from 140? Well, the deviation from 140, how far is 135 from 140? See if you can figure that out before you hear me give the answer. Pause if necessary. Okay, well, that's 5. If the mean is 140, then this is 5 units from 140. What's the mean? What's the deviation here? Figure it out. Well, it's 12. What about this one? From 140 to 143, the difference is 3. From 143 to 137, the difference is 3. 140 and 156, the difference is 16. 141, difference is 1. These are our deviations. And we don't worry about whether they're plus or minus. There are things that we do. If we talk about what's called residuals, we worry about plus and minus. But with deviations, we just write down the absolute value of the difference. Okay, so for the deviation, what we actually did was we took the absolute value of what we get when we subtract the mean from the value. We do x minus x bar and take the absolute value. 135 minus 140 is negative 5, and the absolute value is 5. So this little calculation shows us what we do to get the deviation, and then we square the deviations. Now let me back up a second. We could just average these deviations and get on the average how far each number is from the mean. The sum of the deviations here is 5, 17, 20, 23, 39, 40. Okay? So the average deviation and let's border this a little bit, is approximately, well, is equal to 40 over 6, or about 6.7. So on the average, these things deviate from the mean by 6.7. And that's a good measure of how far the distribution spreads out. Now, if you did that same calculation for this person, what do you think would happen? Well, the deviations would tend to be a lot bigger. The deviations from the mean would tend to be a lot bigger because these numbers are much more spread out. The calculation that we use in statistics, for reasons that you won't understand unless you take a good calculus-based statistics course, is the squared deviation. Well, it's the square root of the mean of the squared deviations. But the squared deviations, well, we just square the deviations. 25, 144, 3 squared is 9, 16 squared is 256, 1 squared is 1. These are our deviations squared. I didn't get that lined up very well, and that's not good practice. The 25 should be over 1 unit, but I'm not going to change it. These are our squared deviations. Now we could call these absolute value of x minus x bar squared. What we're going to do is we're going to add these up. Because what we want, see, we want the square root of the mean of the squared deviations. Now what did we do? First we found the deviations. Then we move back a word and we find the squared deviations. Now we want to find the mean of the squared deviations. What do you think we're going to do to find the mean of the squared deviations? Pause and ponder that. See if you get it right. You should be off the pause now, but hopefully you've paused. Okay, deviation squared. We simply add these up and divide by 6. That'll be the mean of our squared deviations. Now again, these aren't lined up at 5, 9, that's 36, 43. Okay, and 6, 12, 17. I think that the squared deviations add up to 473. And again, that's the sum of the squared deviations. .473. The mean of the squared deviations mean squared deviation is 473 over 6, which is almost 79, 78.83 or something. We'll call that 79. Okay. Then, to get the standard deviation, what do? We take the square root of the mean of the squared deviations. Standard deviation is the square root of, darn it, 79, which is approximately 8.9, 8.8 or 8.9. Get the white out here to make that number clear. And this is our calculation of what we call the standard deviation. This calculation, the 473 over 6, is the sum of the squared deviations over n. So that should be the sum of the squared deviations divided by n. And then what do we do down here? We take the square root of that number. And that's what we get here. The square root of the sum of the squared deviations divided by n, because the sum of the squared deviations divided by n is the average of the squared deviation. It's all summarized in this statement here, and you should practice doing these until you really understand this statement. You should maybe go and compute the standard deviation for the other distribution of blood pressures that I showed you earlier. In any case, this is the procedure for calculating standard deviation.